Hello, my name is Alexandra Ballo, and today we'll be looking at evaluating the performance of calorimeter clustering algorithms for particle tracking. I worked with several colleagues from Youngstown State University and Lawrence Berkeley National Laboratory on this project. Scientists at CERN are recreating mini Big Bangs, and they record these collisions using silicon detectors. The data created by these experiments is projected to progressively increase by upwards of 10 times before 2027. With scientists already processing petabytes of data per year, 10 times that amount simply cannot be pre-processed real-time with their current methods. These experiments calculate the characteristics of the Higgs boson, they search for dark matter, and they look at other pressing concerns in physics. So it is more important than ever to develop some quick method to pre-process their data. Scientists at CERN turned to machine learning and created a project called TrackML that brought together particle physicists and machine learning specialists to solve this problem. The data used in this experimentation included both training and testing datasets. The training dataset had 8,850 events, which were split into 5 files. Each of the events included approximately 10 megabytes of data. The detector used to record this data is built from silicon slabs arranged into cylinders and disks, which measure the position of the particles that cross them. Each detector has a number of detector groups or volumes that are composed of a number of layers. Each layer then contains an arbitrary number of detector modules. The trajectory of a particle present in a hadron collider form a helix because of the magnetic forces present in this type of experiment. So to determine the trajectory of a particle, the impacts need to be matched with the helix that contains the most of these impacts. Following the lead of several of the Kaggle Challenge contestants, we start by assuming there is a small cylinder about the origin which the helix is contained. Then, using the initial parameters given in the training data and creating a special variable to determine whether the helix is clockwise or counterclockwise, we can increment the values of these parameters through all possible combinations and determine which of these helices would best match the hits. The fastest method to group together individual unlabeled collision points from the same particle trajectory is clustering. Clustering algorithms tend to be both faster to develop and run. The first clustering algorithm we'll look at is sparse binning. Sparse binning is an algorithm which assumes that for each parameter, the value set cannot exceed a certain interval. For example, our parameters here, x and y, cannot exceed the interval 0 to 3. We then split this interval into bins. For convenience sake, we'll choose 3 bins here. So each point will receive a bin number for the x parameter and a bin number for the y parameter. When grouped together, the parameters form a small square as shown here. The points within these squares are the points that have the same bin number for both x and y, and they will be clustered together. As you can see, points 2 and 3 share the bin number for x of 1 and a bin number of y of 2, so they will be clustered together. But points 4 and 5 do not share a bin number for y, so even though they are so close, they will not be clustered together. This can cause problems in the future, which is why we included merging as an option for sparse binning. The next clustering algorithm we'll look at is called DV-scan, or density-based spatial clustering of applications with noise. This application looks at a set of points. It picks a random point and sets an epsilon neighborhood around that point. The epsilon is a parameter you can set yourself. Then another parameter you can set is the minimum number of points. If the minimum number of points are contained within the epsilon neighborhood, that point is called a core point. It continues recursively, looking at different points, deciding if they're core points. If they're not core points, but they include a core point in their epsilon neighborhood, they're called border points, and we'll color them differently. When one full cluster is set up, it starts at a new random point and repeats the process. As you can see, there's one point, the purple one in the middle, which is a border point of both cluster 1 and cluster 2. Because cluster 1 was clustered first, that border point is included in cluster 1. Because of this, DV-scan is not a totally deterministic algorithm. The process continues. If a point includes no core points and no points at all, it is included noise. And if a point includes not enough points to meet the minimum number of points, it is also considered noise. This process is repeated until all points have been labeled. After running over 1,000 events, we were able to determine that sparse binning clustering provides an average accuracy of 0.64 in around 4 minutes. The iterative dbScan version improves the score by 3/100, but requires more than double the time to run using our 1,000 iterations. The way sparse binning algorithm divides the space, sometimes it results in dividing very close tracks into separate clusters. However, by merging two sparse binning clustering solutions, the score can be improved by a whole tenth. If the application requires real-time results, sparse binning is better. However, the dbScan accuracy score can be improved by running more iterations. To further improve the computational time, parallelizable clustering algorithms should be considered for this problem. A big thank you to everybody that helped along the way, including XSEDE, Lawrence Berkeley National Laboratory and their Scientific Data Management Group, and Youngstown State University and their Choose Ohio First Scholarship Program. And a special thanks to you for listening to this presentation.